few delegates are still patching in, but we have our two presenters here. So I'll kick things off and get started. So today's webinar will be on long duration energy storage and space-based solar power. So we're really looking to continue the conversation on the key role renewables play and energy storage plays in our energy transition. And yeah, looking forward to hearing from both speakers here today on how different new tech and new configurations and integration in the grid really contribute to that transition. So first of all, welcome to all members and attendees, and for anyone who's maybe their first IPowerE event, just wanted to share a few notes on what our organization is all about. So the Institution of Power Engineers, we enable knowledge sharing and networking between engineers and technicians and operators and other professionals in the energy industry. And we're run by a volunteer advisory council and trustee board, and we have our headquarters with full-time staff in Bedford, UK. So myself, I'm George Cooper. I'm a mechanical engineer with Hatch, based out of Newfoundland, Canada. I'm the deputy president of the IPowerE, and I'll be hosting this webinar today. So we also publish the quarterly Power Engineer Journal and an annual operational report, which includes technical papers and a review of worldwide power plant performance, availability, and reliability. So if anybody's interested to learn more about the IPowerE, you can visit IPowerE.org for more information and upcoming events and membership information. So before moving into our webinar, also just wanted to thank a number of our key sponsors, Spectre Jet Care, Move Lubricants UK, Petro-Canada Lubricants, and Fraser Nash Consultancy. Their contributions help keep the organization running and help us put off events like this webinar and other conferences. So for today's webinar on long duration energy storage and space-based solar, first we have Mark Howitt from Store Electric. We'll be talking about long duration energy storage and enabling the energy transition. And we also have Sam Adlin from SA Catapult, and we'll be talking about space-based solar power. A couple of organizational notes. So there'll be a period for questions after each presentation. So please use the hand raising function in Teams to indicate if you'd like to pose a question, or the chat function, and I can help moderate that and make sure everybody's questions get answered as we move through the question and answer period. And please also mute your mic when not asking a question or presenting, just to keep the chatter and background noise low during the webinar. So I guess we'll move forward. Mark, I can turn things over to you, and if you'd like to start sharing your screen.
Thank you very much. Mark Howitt from Store Electric Limited. This is the purpose of us as a company, to enable renewables to power the grid affordably, reliably, and resiliently. This is about how long duration energy storage will help enable the energy transition. Basically, the stuff that most of us know anyway, that the energy transition must happen very, very soon to stop climate change and hopefully to reverse its malign effects. To the effect that by 2030 we need to reduce emissions by 30 to 45% from a couple of years ago. But it won't happen at all without solving the urgent problem of grid-scale energy storage, because of course renewable generation is not like traditional generation. Essentially, the energy transition replaces hydrocarbons with renewables, which means that technologies must be at the scale and duration of hydrocarbons. It's replacing dispatchability with intermittency. Dispatchability is availability on demand, and intermittency is it generates when it wants to, basically. So power stations are dispatchable. Solar and are intermittent. So is tidal in a different form, and so in a different form is wave energy. So basically that means that you need to balance the energy to make intermittency dispatchable. So effectively you're changing the energy availability from when it wants to when we want. So that's day and night, that's weather-related longer duration shortfalls. The day and night thing, just think, if we are powered by wind and solar, what happens after sunset on a windless winter evening? by 6 o'clock in the evening, all the batteries in the planet are empty. So what do you do for the rest of the evening and overnight? And then you get weather-related weather patterns that extend that for much longer periods. It's replacing synchronous with asynchronous. Now, that needs explaining because synchronous machines are basically large rotating machines that rotate at a speed that's related to the frequency of the grid. There's a mechanical coupling between the speed of the machine and the frequency of the grid, which provides stability for the grid. It provides reliability, resilience, and power quality, none of which are there naturally for a DC connected system. Grid forming inverters can do some of them, but not all of them. So we need to create synchronicity on the grid in the appropriate locations to provide this grid stability, controllability, and power quality. Another effect is that you lose black start capability. Now, a number of people think that batteries can provide black start. Well, they can start themselves. And they say if you add on grid forming inverters, they can start themselves on the grid and synchronize with the grid and create the grid frequency. Yes, they can, but they don't have enough oomph to start much else. Basically, black start is starting the grid from scratch. If you imagine a car pulling another one with a tow rope, when the tow rope goes taut, there's only two things that enable the two cars to move off. One is the torque of the car in front, and the other one is the momentum of the car in front. DC connected systems have neither. AC connected systems, synchronous systems have both. So, and National Grid's distributed restart program proved it. But not if you look at their conclusions. Don't look at their conclusions. Look at the conclusions of the engineering report in the first phase of their development, and that actually comes up with the finding. So renewable generation is on the right scale, but does not do the rest. Most storage on offer is on the wrong scale, duration, cost, and capabilities. So we need storage with the right scale, duration, cost, and capabilities to achieve the energy transition. The solution is geological storage, not anything above the surface. The only thing above the surface is at the right sort of scale is pumped hydro, and there aren't enough valleys for us to want to flood. And those that we do want to flood are far too far away from both generation and supply. So geological storage, storing the energy underground, is the only way that's big enough for this. Storing that amount of energy in metal is just unfeasible and too expensive. So compressed air energy storage uses green air to compress air, green energy to compress air, and which you can then let out again to power the electricity grid. Green hydrogen storage, underground storage. Underground salt caverns are the only way currently known that is feasible to store massive amounts of hydrogen for a period of time, cost effectively. So geological storage is needed for both electricity and hydrogen economies. And this storage can store hydrogen, certainly, for, well, hydrogen and electricity for hours, days, even weeks, and hydrogen for months and seasons, even years. So it's the only one with the scale duration that's appropriate. Now, why are we talking about synchronicity? Largely because of inertia. Inertia is created by large rotating machines. It's the momentum of a spinning machine. Like in the tow rope, it's the momentum of the car in front. And just to give you an idea of the scale, that's a person. So this is a fairly big power station. It's actually a nuclear power station on mainland Europe. But this shows you just how much inertia is needed on the grid. And this is only one small part of the grid's inertia. Then there's the question of energy transition plans. Reading each country's energy transition plans, most EU countries expect to import electricity during times of system stress. Now, time of system stress is when renewable generation is low and or demand is high. And if you look at this map, the ones that were red were already importing by 2019. The ones in orange plan to import by 2030. The ones in light blue plan to import by 2040. Ones in purple claim that they will have enough for their own use and not enough to export during times of system stress by 2040. Now, you can believe that if you believe that the French are going to build 40 gigawatts of new nuclear on time and to cost as of 4 years ago, which is not going to happen, in my humble opinion. Only the green countries will have enough electricity to export during extended times of system stress. And Norway has legislated that they will be able to turn off their interconnectors in such times. And I've even had the Swiss question whether or not they'll have anything to export and actually needing to import. So there's not a whole, if everyone's importing, who's exporting? And if nobody's exporting and everyone's depending on imports, that means that interconnectors are going to fail. And that means blackouts for any country that is relying on interconnectors. And as I point out, we've been relying on imports through interconnectors since 2019. So we need to store energy to keep the lights on. And that means large-scale, long-duration storage, multi-gigawatts, up to 2 weeks in every single country, or at least assigned specifically to that country. So we could store in France, but only if that storage is dedicated to the UK market, rather than subject to export conditions. Reason I say that? Well, thanks to Vladimir Putin, we have had proof that when push comes to shove, even within the European Union, even the most community-minded Germans will switch off their gas interconnectors from the neighbouring countries when they feel that they don't have enough for their own use. Thanks to an almost concurrent dearth of nuclear power in France, the interconnectors to France all went into reverse. Those two things proved that when push comes to shove, in the energy transition, you cannot rely on interconnectors, because which grid operator is going to tell their government, I'm sorry, that blackout in that major city was because we were exporting the energy it needed to keep the lights on? Another factor is the scale of the grid. Now, that's a bit of old information. $2 billion of grid reinforcement per gigawatt of new wind connected by 2030. The latest information from before Christmas, I've got to update this. Every new gigawatt of offshore wind requires £3 billion of onshore grid reinforcement, ignoring the grid connection itself. And that is completely unaffordable, bearing in mind that we are looking to move to at least, I think it's 118 gigawatts of offshore wind. And that's before you consider the amount of offshore wind that's required for the hydrogen. So that's a completely unaffordable thing. £3 billion per gigawatt of new offshore wind. Breakthrough Energy did an analysis a couple of years ago in America and said that the grid needs to more than triple in size. I think it was 3.5 times the size, purely to absorb the renewables, purely for electricity use, ignore hydrogen use. And they concluded that that's too expensive for the USA. So therefore, if it's too expensive for the Americans, what hope do we have? McKinsey say, and I quote, "The energy transition will require a dramatic increase in capital spending on the electric grid, delivered at an unprecedented pace." And that I don't see happening anywhere much in the world. So we've got to solve that problem. And then there's another one. There's curtailment, which increases with renewable penetration. And various studies have shown that as renewables account for a greater percentage of electricity on the grid, so curtailment shoots up to unmanageable proportions. And it's largely already there in the UK, to the extent that some years ago they excluded curtailed energy from CFD contracts. Then there's there's the non-energy costs of the electricity transition, of running the grid. These are the costs of balancing services, ancillary services, such as stability, power quality, and things like that. Now, a good proxy for that is BSUOS, Balancing Services Use of System. And the costs for those, once we crossed the threshold of about 16% of renewables, started skyrocketing, to the extent that in just 3 years, they increased by a factor of 14 times. And every forecast has been exceeded greatly. And in fact, that 2021 to 22 forecast was exceeded so much that they agreed with the government to defer until this year some of the BSUOS costs. Now, no one's confessing as to the fact that the BSUOS costs now are even greater. Every single grid will have these challenges. I've put it when we exceed 16% of demand, but there is a condition on that. It's only 16% in the UK because we already had 3 gigawatts of pumped hydro. If you've got more pumped hydro, then you can take a higher percentage before it starts escalating. If you've got less long duration storage, then you can take it starts escalating at a much lower percentage of renewable penetration. So what is the effect on bills? Electricity bills used to be somewhere between 75 and 80% wholesale energy costs and 20 to 25% system running costs. Now it's inverted. 38% wholesale energy and 62% system running costs. But that's just the superficial thing. You look down at what wholesale energy is. That also includes system charges. And the system running costs are rising exponentially. So essentially, we are down to the level where those top percentages are inverted. The cost of electricity is less than a fifth of the price of electricity. We think that the Putin premium is to blame for escalating electricity costs. I put it forward that the Putin premium is merely a mild effect compared with the energy transition because of the lack of storage on the system. So a summary of the increased costs of the transition, very broad brush, are roughly 25% for balancing energy, 25% for system operability, and 50% for network reinforcement. Down to more grid, down to congestion and to curtailment. And these numbers will vary by jurisdiction. So the limitations of, we focused on compressed air energy storage because we saw that the need was geological storage and nothing else is at the right scale and duration. We focused on it as being too inefficient, so we created an adiabatic version and a diabatic version, both of which are significantly more efficient than the traditional stuff. Emissions were too high, great big fractions of the emissions of a power station, which we eliminated with the adiabatic, and the diabatic one made dual fuel so that it will decarbonize as the grid decarbonizes. previous adiabatic case failed. We're using obscure and expensive thermal storage and stuff that destroys itself. So we perfected that in all of those factors and perfected the integration of that with the power and air subsystem. Unfortunately, I can't go into that in a public presentation. Limitations of scale due to using salt caverns for air storage. Those are more perceived limitations than actual, but we will develop other geologies. But those other geologies will always complement salt cavern storage. The reason I say that is because salt caverns are a nice cavity. If you use, for example, depleted hydrocarbon wells or aquifers for storage, that's more like a sponge compared with the cup of salt caverns. Holding water in a cup is good for quick in, quick out, short duration. A sponge is far better for slow in, slow out, long duration. They complement each other. Batteries just cannot do the job. They are inefficient, and those numbers are not numbers that you'll recognize. The reason why is because I'm looking at them grid to grid, lifetime average. Most batteries quote 85 to 92% efficiency, terminal to terminal, day one. To go from terminal to grid, you are adding on the cooling, which is about a 10% penalty in the north of England, and much worse when you get into hotter climates. And the power conversion, which is about a 5% penalty, AC to DC and back again. And these are generous numbers. So that's 15% penalty. The effect of lifetime average is that over the 8 to 10 year life of the batteries and the electronics, both of those numbers will triple. So to get your lifetime average, you need to double that 15% penalty. And you've also got to manage a rapidly deteriorating asset. Cost effectiveness at scale and duration is a lot better because of the scale, duration, and plant life that it offers. The plant life being 5 times that of batteries with midlife refurbishment. But the big issue is how many jobs they can do. Because the fact that CAES and in fact all other large-scale long-duration energy storage, be it gravity, pumped hydro, they're all synchronous, naturally synchronous. So we can deliver all of these services concurrently, whereas each would require a separate battery, even if the battery can't do some of them like black start. Then we start to solve the problem of having to build so much grid. This is the issue of £3 billion worth of onshore grid connection for every gigawatt of offshore wind. If you build it behind the meter for the renewable generation, you're taking the power from the renewables, can be single or multiple sources, goes into the storage. So the storage absorbs the intermittency and puts out only what's required, which means that for offshore wind, your grid connection can be reduced by 50%. For onshore wind, it can be reduced by about 2/3. For solar, it can be reduced by something like 5/6. Not only that, but the onshore grid is sized for peak demand. What you're putting out is peak demand. So therefore, the effects on the onshore grid are radically greater than that, the benefits. Then we looked at hydrogen. Limited storage capacity. A lorry carries 3 tons. Whereas salt caverns, identical salt caverns, this is why we looked at it, identical salt caverns, albeit with different metalwork, better metalwork, can store 10 million tons, which is a radical difference in the amount of storage. Yes, you can have gasometers, but they're only going to be in tens, maybe as much as hundreds of tons of hydrogen. We're talking about tens of millions here. Different order of magnitude. Electrolysis hates intermittent power. Lots of people talk a great deal about truly green electrolysis being coupling the electrolyzers directly to the renewable generation. But that reduces the electrolyzer efficiency, it reduces electrolyzer life, and you need 3 to 6 times as many electrolyzers per ton of output, hydrogen, as compared with powering the thing from baseload electricity. So, for example, if we're powering our electrolyzers using offshore wind from the southern North Sea at a load factor of 40%, you need 2.5 times as many electrolyzers for the same output, ignoring the efficiency reduction. Whereas we can deliver near baseload or baseload electricity to the electrolyzer, and we can do so thoroughly green. And we can do so without the grid connections as well. Hydrogen is usually considered standalone, but we've found that it's best in complex multi-capability schemes. Electrolysis technologies are too small. So we've also developed a high temperature electrolysis patent, which we will develop sometime soon, which uses the heat of compression to catalyze electrolysis at large scale. So the hydrogen economy, not just electrolysis, hates intermittency, which reduces hydrogen plant life and requires much more asset investment, as I've just said. So it applies to the whole hydrogen economy: electrolysis, the fuel and chemical synthesis, the ironworks, the steel works, and also to the electricity economy, such as desalination and water treatment. All of those, they don't want intermittency. They want something close to baseload power. So we can solve this by removing the intermittency before the plant, storing the output in adjacent caverns or stores, supplying the consuming electricities with both electricity and hydrogen, and those would vary in a synchronized way, if they vary at all. And we can do all of that at grid and infrastructure scale. And this is the same diagram, essentially, with the renewable generation going onto the grid, but also with output into electrolysis, into, for example, nitrogen capture, ammonia synthesis, and then onto whatever plants use it, or output onto the gas grid. But then you can remove the enormous costs and regulatory complexity related to a grid connection. You can just cut that grid connection and run the entire hydrogen economy off grid. And that will transformatively improve the costs of the hydrogen economy, while at the same time avoiding the needs to excessively reinforce the grid at such enormous expense. And that enormous expense is growing greatly. In just in about a space of a year, that cost of grid reinforcement increased by almost double. So that is how large-scale, long-duration electricity storage, both and hydrogen storage, can enable the energy transition and renewables to power the grid affordably, reliably, and resiliently. Thank you very much. Any questions?
Thank you, Mark. If anyone has any questions, if they'd like to raise their hand or use the Q&A function as well. Yeah, just opening the Q&A window at the moment. I see there's a question on making the presentations available. I think in this case, some have asked for the presentations not to be made available to be downloaded after, but we can check that after the webinar further. And in terms of recording, I know there was a question with that earlier. I know this webinar is being recorded, and I think Christine can help us share some information on where that may be available after the presentations. Hey, Ronald, do you have a question if you'd like to go ahead?
Yes, I'm very interested to hear what you have to say about conventional power, whether the role of gas turbines, combined cycle plant, and so on.
Sorry, what's the comparison between?
No, I would like to hear your comments about the use of conventional thermal power in conjunction with the systems that you proposed, for example, gas turbines and a combined cycle.
The conventional power addresses half of the issue, which is the output side of energy. So when there isn't enough energy on the system, it will generate. But it won't do anything about the input side when there's too much renewable generation. So it only addresses part of the problem and therefore necessarily adds a significant amount of cost that is not generally imputed against the generation. In addition to which, every power station has its emissions. That's emissions. If you base it with CCS, what the CCS people don't like to confess is that it imposes somewhere between 30 and 40% inefficiency on the power station that is hosting the carbon capture equipment. They also tend not to pay for the carbon dioxide transportation and storage. There's also lots of hazards in relation to carbon dioxide that I'm not convinced have been fully accommodated. So there are an awful lot of costs there. And even then, the efficiency of carbon capture is way below what is needed. Now, if you look at the Boundary Dam power station in Saskatchewan in Canada, that was built to capture 90% of carbon dioxide and sequester it. Now, not only has it proved very fallible as a plant, but its actual capture rate has varied between 30% and 80% at far higher costs than expected. I'm not sure that any other, I'm not aware of any other CCS projects having published their output. And even if it were to capture that 90%, you would still have to put in some negative emissions technology like BECCS or direct air capture to accommodate the other 10%. So the overall system costs of running residual thermal power are absolutely enormous. Some people are proposing that you'd keep this residual generation capability sort of in reserve only for use in weather periods like the Dunkelflaute, when you've got virtually zero generation for a fortnight, that sort of weather period. Well, then how do you pay for it? How do you make sure that you're turning the machines and they're not seizing up and that they're available when you put in the generation? How do you make sure that the fuel is still there and not leaked out or whatever else when it's actually needed? How do you keep your supply chains going when your utilization rate is below 5%? Probably in that sort of scenario, way below 1%. So there are all sorts of questions that would be raised by continuing to use traditional generation. Does that answer your question?
Yes, thank you. That's most appreciated.
I guess I could ask a question as well, maybe as a follow-up to Ronald's question with with hydrogen production and storage being a key piece of this picture. I was wondering if you have thoughts on in terms of reconverting hydrogen back into to energy and power on the grid. How the combustion turbine, reciprocating engine, thermal type conversion methods fit in versus the the hydrogen fuel cell method of converting energy. I know they have very different efficiencies, but of course very different costs and scalability as well.
Basically, that's going to be an economic analysis. Hydrogen-fired power stations are about as efficient as natural gas-fired power stations. They're almost there. They will be there soon enough. That's just a matter of technical tweaking and development work. Whether or not you can scale up the fuel cells to sufficient scale, that is an entirely different question. At the moment, they are far more geared towards a small scale, possibly as high as the medium scale, but I don't think that they have any hope for the time being of hitting the large scale. In terms of the uses of the hydrogen economy, I think that we're getting it all wrong. The last thing we should be using it for is heating homes and buildings, because hydrogen is about the highest enthalpy form of energy, and sensible heat for domestic and commercial purposes is about the lowest enthalpy energy. And you're wasting all that enthalpy to convert between the two. It uses, even the Hydrogen Association, they admit that heating a home with hydrogen takes 6 times as much energy as heating it with a heat pump. So I do not believe that that is the way forward, apart from specific use cases. On the other hand, I don't believe that powering vehicles with electricity is the way forward for the majority of our energy. I think 2/3 of vehicles of all sorts need to be hydrogen powered, and that would account for, say, 90% of all transportation energy used. Why? Only 40% of houses don't have a dedicated parking space. Many of those houses, the 60%, don't have as many parking spaces as vehicles. So you can't leave the thing charging overnight. You can't leave it connected to the grid to deliver vehicle to grid. There isn't enough elemental lithium in the Earth's crust for the vehicles of this world, let alone the power systems of this world, the portable devices, the lightweight alloys, the catalysts, and all the other wonderful uses that we have for lithium. We need to use the right technology for the right thing. And we need to get hydrogen to a point whereby it overcomes the introductory cost down that batteries did before. In addition to which, there's the benefit that to refuel a hydrogen vehicle takes not much longer than a diesel vehicle.
Right,
But there are enormous uses for hydrogen in industry of all sorts, both chemical and mechanical. So, for example, iron making, steel making, as well as all the precursor chemicals and artificial chemicals that you can make out of hydrogen. So there's a huge benefit. And ultra high temperature heating, industrial scale heating, that could use hydrogen, although there's still limited use for electricity, for example, in electric arc furnaces.
Yeah, thank you. I like the comment on the outlook on electric vehicles and the amount of lithium in the Earth's crust. That's a good question we should be asking ourselves before I think we called those Fermi questions in the academic days. So, yeah. Any other questions? I did have another in mind myself, but wanted to give everybody else a chance as well. Yeah, if not, another question I had, generally looking at different grids for the UK grid, for example. I'm not sure if this was clear on one of the presentation slides, but do you have a feel for the amount of energy storage we need in the system? And in that system, I imagine it's fairly system dependent in terms of the participation of renewables and thermal stations and dispatchable generation. But I was wondering if you had some thoughts or insight on that front.
Well, it's entirely dependent on how you do it. If you do it the way we're going to do it, we're going to need far more storage than we can deliver. well, actually, the amount of storage we can deliver is not a constraint. NIMBY is amazing. But if you deliver it in a logical, sensible, well thought through way, you need an awful lot less. I'll give you an example. If you develop your integrated systems, if you have your ammonia synthesis plant entirely separate from your hydrogen plant, you'll need a lot of hydrogen storage. But if you integrate the two plants and integrate them with the electricity storage so that they're varying in tandem with each other with the renewables and the amount of electricity storage capacity that remains at any given time, then the plants are flexing up and down concurrently, and the amount of intermediate stocks you need are minimal, comparatively minimal. So it depends enormously on how you do it. Then there's also what I've outlined in terms of the comparison of the uses of hydrogen and electricity, for example, in heating and transportation, but also in industry, suggests that the current ratio of half of our energy is natural gas, quarter is liquid hydrocarbons, and a quarter is electricity. That's the ratio as of about 5 years ago. That's going to be inverted. So at least 2/3 will be electricity and 1/3 hydrogen. So that assumes that you're electrifying the right things and you're hydrogenizing, forgive the word, the right things. But if you're doing the wrong things, then it's going to be totally different. So there's an awful lot of central planning and intelligent planning and broad-mindedness needed. And the skills that we've got in the IPowerE and other engineering institutes are exactly what we need in order to do that sort of thinking.
Mm-hmm. Much agree. And I guess another example of a good point on the how you do it and how you approach the energy storage. In my experience, I've worked more of the isolated grids. So an example, a mining project where we're burning diesel as the main fuel source at great cost. A number of years back, they were looking at bringing wind power to the site, and a study was done, but the study went on full bore on a very large wind farm and very large battery storage system, and quickly came to the conclusion that there wasn't really a business case or a cost-effective business case for levelized cost of energy for wind power at the site. But then kind of went back and said, well, wait a minute, but yeah.
But there would be if you use large-scale long-duration energy storage.
That too. But I guess when we brought it back to a more moderate-sized wind farm and a smaller battery storage system, is really just enough that would allow us to take one generator set offline and give us time to bring up the diesels and respond in terms of a shortfall with wind. All of a sudden, there was a business case and there's something strong enough there they've been able to go ahead with the project. So yeah, that each system and each application and how you approach the energy storage can be very, very important there, and certainly longer duration options that are more cost effective could be of interest up there in the future as well. So, and
then also you need to fill up their power stations, and if you've got electrolysis on site adjacent to this locally produced renewable power and electricity storage, then you can satisfy the rest of the local economy as well, even if you're 2,000 miles away from the nearest grid connection.
Yeah. I was looking to circle back to a few questions. I apologize for missing. I'm not sure if they were just delayed and popping up, but back to the long duration energy storage presentation. I saw Gary Locke, you had a question on using hydrogen CCGTs. Would you like to go ahead with that question?
Thank you. My question was, you said that it's a totally green way of producing power by storing hydrogen and then releasing it through CCGTs. It is if you can eliminate NOx, and also there is the potential, there will be a release of hydrogen either somewhere in the storage or somewhere in the transmission hydrogen will leak. It's just a fact of life, both which are detrimental to the environment. So it's not a totally green solution. It's a greener solution.
I would agree. It's not perfect. No human system is. With regards to NOx, all the big turbine manufacturers are making enormous strides into reducing NOx, and they have discovered that it's in the fine points of the control of the turbine that would reduce the NOx, and they are, as I say, making great strides. I have no doubts that that will be greatly reduced, and even then it can be scrubbed, as it is at the moment off power stations. With regards hydrogen emissions, well, let's look at the methane economy. You can have leakage of 20% of methane, as they do in Russia, or you can have leakage of fractions of a decimal of a percent of methane, as they do in places like Sweden. It depends on how well you make and maintain your systems.
I also saw that Charles Turner had a question on the salt cavern storage and hydrogen atom permeability. Charles, would you like to go ahead with that question?
Yes, good afternoon. By the way, excellent presentations. Really appreciate this. Unfortunately, I came in a bit late on the first due to Teams issues. Maybe it was addressed, but I know we've had struggles just maintaining hydrogen storage at combined cycle and thermal stations for generator cooling, and battling the permeability of the hydrogen atom for storage. How would this permeability, does it impact the ability to store in a salt cavern? I'm just wondering and how the characteristics are in comparison to compressed air storage.
Salt caverns are exceedingly hermetic. To my knowledge, there have been no detectable leaks from salt cavern storage in the last 2 or 3 decades. It's very different from storing the hydrogen in metal. Does that answer your question?
Yeah, I mean, you've addressed it from storing it in metal, yes. But I'm just wondering what's the characteristic of a salt cavern that makes it beneficial with respect to the hydrogen storage? Is it is it just that it's I'm not sure. In Ontario we've got some smaller compressed air energy storage systems installed currently, and that was one question that did come up on alternate on the hydrogen side.
Well, to go through the making of a salt cavern, what you start off with is a geological layer of salt. You make the salt cavern by drilling into that layer of salt, pumping in water, dissolving the salt, pumping out brine, and what's left is your cavern. And it's naturally hermetic. The reason it's naturally airtight is because salt is very much like glass. You will know that glass is not solid, it's a supercooled liquid, and yet it's harder than concrete, much stronger than concrete. You've walked up glass staircases that are much thinner than an equivalent concrete staircase. And yet, if you look at an ancient window side on, you'll find that it's pear-shaped because the glass has flowed downwards. Salt is much the same. It flows over time and under extreme pressure. That is geological pressure, the pressure of the weight of the rock above it. That means that if it develops any cracks, it will seal them. And when this was originally tested in the salt mine at Winsford, they deliberately created cracks by an explosion within a small salt cavity, and the next morning the cracks had vanished, because the flow of the rock had filled in the cracks. Now, as long as you keep the right pressure of air inside or of hydrogen inside the cavern, that maintains the cavity. So this flow of rock will affect effectively the edge of the cavity and the surroundings of the cavity. And so when they did the midlife deep inspection of the Huntorf plant in Germany at the age of 29 years, they found that even though the sides of the caverns had moved by between 1 and 2%, the structural integrity was at the same as day one. So effectively, a well-managed cavern's operational life is indeterminate. So, or in layman's terms, eternal. So it's also exceedingly inert. It doesn't react with anything very much, which is why the biggest use for salt caverns in the United States of America is for storing special waste, which in layman's terms is the stuff that you don't want to ask what it is. So it's very inert, very good structural integrity, enormous strength, and it will fill in all its own cracks. Self-healing is a technical term, I think.
Yes, very good. Okay, thank you very much.
You're welcome.
Maybe as a follow-up question, which I think Charles's question was going in the direction of, is for salt caverns, with all their benefits and suitability for the application, is there a known or anticipated leakage rate, based on the size of the cavern and storing hydrogen?
Well, about a third of the natural gas stocks in Europe are in salt caverns, identical salt caverns, the only difference is being the size of the tube and the metalwork going upwards. And there's never been an underground disaster in them, and no detected leakages of which I'm aware. They are naturally hermetic. With that flow of salt, I remember when they were exploring the oil and gas in the pre-salt field off the coast of Brazil. They declared they cannot stop the drill for more than 3 days, because if they do, the salt will have flowed around the drill so much that it seizes the drill, and not only have you lost your well, you've also lost all the equipment in it. So it seals around your casing.
Very interesting, thank you. There any other questions on the line for Mark or Sam? Yeah, if not, I suppose we can proceed to wrapping up the webinar today. So just want to send a thanks again to both to Mark and Sam for presenting all very interesting presentations, and definitely to me it gave me a new way to look at the grid and energy storage and the future of solar. And yeah, I'll definitely keep following those spaces as an organization, and hope to see continued good progress in the future. Sorry, actually, I just saw another question from Gary Locke. Do you have another question, Gary?
Yeah, sorry, I might have missed it, but
Okay.
I was just wondering how many sort of viable locations we have in the UK for salt caverns.
There are 5 major salt fields in the UK. The smallest one is in Lancashire near the coast, but it extends substantially offshore in the Irish Sea. It gets extended eventually to onshore in Larne in Northern Ireland. And the south end of that gives a major outcropping in Dorset. The Cheshire Salt Basin is very famous. That's the second biggest in the UK, but the biggest salt basin in the UK stretches from north of the Tees to south of the Humber, and from the Vale of York to Lithuania. And that's when we are using salt caverns for the storage. Once we have some plants up and running, we will also develop other geologies, which will open up other locations throughout the world. And this is where it comes back to what I was saying in the presentation about different geologies, the holding the water in the sponge compared with holding the water in the glass. The salt cavern being like the glass. The other geologies, the porous rock geologies like aquifers and depleted hydrocarbon wells, they're like the sponge. Much bigger capacity, much longer durations possible. different applicability to air and to hydrogen, but those need exploring.
Thank you.
All right. Thanks again, all. And if there's no further questions, thanks also to everyone for attending. And definitely good to see a good number of attendees and good discussion today on this webinar. Look forward to seeing more of you all at the next events and webinars in the months ahead.
Thank you very much.
Yeah. Thanks also. I guess we'll close the webinar session today. Yeah.
Thank you, George. We much appreciate your work there.
Yeah, no problem. My pleasure. And I did take a number of screenshots during the session, so Sam and Mark, I can share with those with you afterwards. And I think our main office will be in touch on how to access the recording if it'll be made available afterwards.
Thank you.
Thank you. Cheers, everyone.
Yeah. Cheers, all.
Thank you, everyone.